Okay, so let's get started again. So we saw what's when you combine two waves, if they have the same sign, then you get a resultant wave that is bigger than either one of them. And if waves have opposite signs, the resultant wave is smaller than the biggest wave. This is called destructive interference, and this is called constructive interference. And of course, if the two combining waves had the same size with opposite sign, you can get complete destructive interference. Okay, so the wave would be zero at that point. Okay, so we'll see. Now we'll combine sinusoidal waves. Okay, so here's how it looks mathematically. So here's a sine wave. Now what we're going to do is we're going to keep things simple. We're going to combine waves of the same wavelength and frequency. And that's what we're mostly interested in. But now see, what we are going to do is we're looking at waves traveling in the same direction. So you have both waves traveling in the same direction. Phi is called the phase difference, okay? And so the phase difference tells you, so if the phase difference tells you the following. So okay, so the phase difference tells you the following. Okay, so let's say one wave at t equal to 0 at time t equal to 0 is starting there, and the second wave, if it's traveling starting from there, this guy is related to the phase difference. So that's what this is. Okay. So we have two sine waves of the same frequency and wavelength traveling to the right. Okay. So from this diagram, you can see that when phi is 0, so they're traveling starting at the same point. So the phase difference is 0, and they will combine to give you a wave of amplitude twice as much. When the phase difference is pi, so when this wave was like there and that wave was over there, when the phase difference is pi, they will combine each other and completely give full complete destructive interference. Okay, so if you have two waves, pure tones traveling from speakers that are in opposite phase, this is called opposite phase, and you'll get no sound. Okay, at that location. All right, and this is for a phase difference of 2 pi by 3. This is how they combine. Okay. So again, for a phase difference of pi, you have the waves completely interfere destructively. Okay, so we saw that. Now, here's a technique that you might want to at least have heard about. This is when you have to combine several waves, then this technique is useful. Okay, so let's go over that. Okay, so for instance, okay, so let me remind you about vectors. Here's theta, here's the vector, and the y component of the vector was given by ay was a sine theta. Okay, so you see, for the wave, it's a sine kx minus omega t. So it's like there's the amplitude of the wave, and it's giving you the y component, the y position of the string is given by the y component of this vector. So what we do is we draw a phase, we represent the wave by this vector A, and the angle will be kx minus, the angle will be given by kx minus omega t. As t is increasing, you see as t is increasing, this angle is increasing, okay? And the y component of this vector, this phasor, is giving you the wave, okay? So now it's if you want to combine several waves, here's what you do. Okay, so for instance, if you want to combine two waves like this, so y equal to y1 plus y2, and y1 is a1 sine kx minus omega t plus a2 sine kx minus omega t plus phi. Here's what you do. Here's how you combine them. Here's a1 and a2. You draw this vector a2 like that, and this is the phase difference phi. Okay, and there would be the resultant and the component of the y component of the resultant. That's your combined wave. Okay, so that's how you do this combination. So that's how phasors work, and that's what's shown here. Okay, so y is a so here's y1, and here is y2. There's y2. And there's the resultant wave, and you would calculate this resultant wave. That's the amplitude of the resultant wave, and there's an amplitude of the resultant wave, and beta would be this phase. Okay, so that's how you add the phasors. Okay. Now this technique is useful when you have to combine multiple waves. Okay. But I just want you to have seen it. We won't be using this too much, okay? Okay, so now what we want to see is how waves reflect when they encounter a different media. Okay? And this will be useful in understanding stuff like this. So when you deal with thin film optics, so for instance, if you want to explain phenomena like this, so look at this airline window, you can see the different colors, and you want to see how did those colors arise, because the airplane window itself doesn't have those colors. And so here's a thin film of oil on water that's producing all those colors, and you want to see how those colors arise. Some of these butterflies, their wings are not colored, and you want to know how, you want to see how the colors arise. Okay. So, so here is a, so we simplify this subject, and here's how we'll deal with it. Okay, so here's a string, and this end is attached to a wall. You send a pulse down, and this wall will reflect this pulse. And when it reflects this pulse, you see the positive pulse has become a negative pulse. Okay. And if this end were free to move, a positive pulse upon reflection remains positive. Okay. So let me show this to you in as a simulation. Okay. So here's a pulse. Okay. And this pulse, when it's reflecting off a fixed end, it becomes a positive pulse. I mean, it switches sign. And if the end were free, a positive pulse remains a positive pulse. Okay. And for instance, so this is not just academic interest. So if for instance, air, water. So if a light wave reflects off a water surface, the water surface is acting like a fixed end, and the water surface is acting like a fixed end, and so this pulse, a positive pulse, will become, upon reflection, will become a negative pulse. Okay. Now, if on the other hand, a wave starts off in water and it's reflecting off the air interface, this positive pulse upon reflection will remain positive. Okay. So, so that example that we see shows up in various places like that. Okay. All right, now we'll come to the subject of standing waves. Okay. So to create standing waves, what you need is identical pulses. Okay, so see, the pulses have the same amplitude, they have the same frequency, except that one is traveling to the right and one is traveling to the left. Okay, and this kind of stuff happens in musical instruments. So you have two identical waves traveling in opposite directions in the same media. And let me show you a simulation. Okay. All right, so here's a wave traveling to the right, and here's an identical wave traveling to the left in the same media. And when they combine, you see you get a wave that's standing. It's not traveling in either direction, and this is called a standing wave. And this is what will happen in a musical instrument. So when you pluck a guitar string, one wave travels to the right, and it's reflected on the struts and comes back. And so on the string, you have two identical traveling waves traveling in opposite directions. What that ends up doing is creating standing waves on the guitar string. Okay, so the guitar string, a given length of string, can either vibrate in this mode, that mode, or that mode, okay, or a higher harmonics. So guitar string can only vibrate at certain frequencies. Okay, so here's a string fixed at both ends, and these are the standing waves. You send a wave down to the right, it gets reflected to the left, and so on this string you have standing waves created. Okay, so here's a wave with two nodes, three antinodes, number of antinodes, four antinodes, and so on. Okay, so those, so the string can only vibrate in certain at certain frequencies. Okay, so again, standing waves are created by two identical waves traveling in opposite direction in the media. Again, when you combine the two, you can use trigonometry to combine the two, and you see here the phase depends on both the space and time coordinate. Now the phase in a standing wave, the phase depends only on the spatial and or only on the time coordinate. Okay, so that's a standing wave. So standing waves are set up by superposition of incident and reflected waves on a string at both ends. So now, so only for resonant frequencies are the natural frequencies of oscillation of the system. So the natural frequency of oscillation for this string are these. Okay. So the frequencies, the natural frequencies, are given by n times v, the wavelength, the velocity of the wave, and the velocity of the wave is given by the tension in the string divided by the mass per unit length. And L is the length of the string. Okay, so the frequencies at which this string can vibrate are given by those, and n are integers. So this string can vibrate at this frequency, that frequency, that frequency, and so on. So if this is 50 hertz, that's 100 hertz, that's 150 hertz, and so on, corresponding to n being 1, 2, 3, and so on. Okay, so the frequency of normal mode form a harmonic series, and so the frequencies are n times the fundamental frequency. Okay, so all right. All right, so for a string fixed at both ends, the allowed frequencies are integer multiples of the lowest frequency or the fundamental frequency. Okay, and the frequencies are given by n times divided by 2L times tension divided by mu. Okay, so when you play an instrument such as a guitar and so on, okay, the guitar has 6 strings, so you have one of 6 strings to pluck from, and the way you play different frequencies is you can choose which string to play, pluck. The tensions are all set up in the strings beforehand. Okay, so while playing you don't change the tension, but your choices are to play which string and then change the length of each string. And that's what you do when you're moving your left, if you're a right-handed player, when you move your left hand back and forth along the strut, you're changing the length of the string. So that's how come you're producing different frequencies. Okay. All right. Now, let me, drum head is slightly different. The frequencies do not form a harmonic series. So here's a drum head, it's not vibrating. And so, well, okay, so this is vibrating, and the next higher frequency is 1.5 times, 59 times the lowest frequency. And this second mode is 2.14 times this lowest frequency. So they're not forming a harmonic series. And let me show you how a drum head vibrates. Okay, so there's the lowest frequency. And as you hit different spots, and so there's the non-vibrating drum head. Here's a different mode. Okay, again. So as you hit different spots on the drum head, you set up different modes. Okay, so go and play with the simulation. It's quite cool. Okay, so those are the different modes of vibration of the drum head. Okay, and they do not form a harmonic series. Okay, one of the famous mathematicians of the 20th century is asked the following question. Let's say, so this is a drum head, and you can have different shaped drum heads. He asked the question, can you just from hearing the drum figure out the shape of the drum head? Okay, and you can go to this link and read about this problem. And here's so here is can one hear the shape of a drum? So this was a famous question. As the title of 1966 article by Mark Cack. So here's Mr. Cack. He asked the question, and it turns out that the frequencies, these are called the eigenfrequencies of oscillation. These frequencies depend on the shape of the drum. Okay, so the answer to that question is a partial yes, but it turns out that so in a for a two-dimensional drum, now mathematicians will of course generalize the problem to all cases. So for two-dimensional shape, okay, so apparently, so it turns out that these two drum heads would produce the same frequencies. Okay, So you couldn't tell the difference between these two drum heads if you had your eyes closed. And now the thing is, it turns out that these two drum heads have the same perimeter and the same area, okay? And so here is a series of drum heads that have the same frequencies, eigenfrequencies, so you couldn't tell those apart. So for instance, you see, you can change the shape. This is how the shape of the drum head can change, and they would produce the same frequency.
I couldn't quite hear you.
Okay.
Could you?
Okay. So within a certain limit, so you can certainly tell the difference between this drum head and a circular drum head. Okay, so that finishes this chapter. And what was this? This was chapter 16. So we have one